an introduction to the Temperley-Lieb loop model. So if you were here last week, you'll recognize the first 10 or so slides. If you weren't here last week, I'll be going quite quickly through those slides, so I hope that it's still understandable. So this is work that I've been doing with Jan de Geer and Jesper Jacobsen. It's about the Temperley-Lieb model and calculating a particular observable in that loop model. So in case you're not familiar with loop models, the first couple of slides is just pictures to give you an idea of what the loop model is about. So we're working on a square lattice which has periodic boundary conditions or reflecting boundary conditions. So that's just on a strip. And on each face of the lattice, we draw loops in one of two configurations, so either like that or like that. And then, obviously, when the square's neighboring, then the loop follows goes through. And in the reflecting case, if the loop comes to the boundaries, then it just reflects into the next row, which is where the name comes from. Okay. Oh yeah. So this is on a semi-infinite lattice. So we have the top is just fixed at 0, and then the bottom it goes off to negative infinity. There's some there that you might not be able to see. So as an example configuration of this loop model, in the reflecting case, and generally we're only interested in the way that the loops connect at the top. So in this case, the first site is connected to the second site, the third site is connected to the sixth site, and so on. So we can take this information and just represent it as what's called a link pattern. And what this means is that we're ignoring the paths that the loops take. Just however the loop gets from one point to the other, we don't care about that, only care that it gets there. And the second thing is that we're also ignoring closed loops. And these are the two rules that are given, that are described perfectly by the Temperley-Lieb algebra, hence the name, the Temperley-Lieb loop model. So the Temperley-Lieb algebra is generated by these EI, and before Vladimir says anything, I have used I to also mean the imaginary number, but in one place. So EI, we have an EI for each site of the lattice. So in the Sorry, no, I said the same thing last week. We have an EI for each pair of sites, every neighboring pair of sites. So in the periodic case, we have L of them. In the reflecting case, we have L minus 1. But in the periodic case, we're also understanding that L plus 1 is the same as the first site because they're neighbors. So the first relation is that you square it to get itself back multiplied by some constant. And the second relation is this. And for the sake of the loop model, the best representation to choose involves drawing EI as this picture, acting between sites I and I plus 1, so between neighboring sites. And if we represent EI as this picture, and multiplication means concatenation of the pictures, so multiply on the left, that means you concatenate the picture onto the top. So here we have EI times EI is equal to tau times EI. You can see that what this means is that we're taking this loop away at the expense of a factor of tau. And the second relation here is EI plus 1 EI gets replaced with just EI, and that means that we're ignoring this curly path and just only caring that this point is connected to that point. So that's the same as that point connected to that point. Okay. So back to the link patterns. So the Temperley-Lieb algebra acts on these link patterns, which are the things that I mentioned before. So a link pattern or perfect matching of L sites. So that means that we have each site has to be connected to one other site without any crossings. In the case that L is odd, there will be a single site that is unpaired. And in the reflecting case, which you can just use this picture, in the periodic case, we can also represent it that, but understand that site 1 is to the right of site L. But in that case, we can also represent it as a link pattern, a chord diagram on a circle, in which case L is explicitly to the right of 1, the left. But you can also think of this as looking down the semi-infinite cylinder and seeing where all the loops are connected in the cylinder of the lattice. And so you can convince yourself that these two link patterns are actually the same in the periodic case. We have 1 connected to L, 2 connected to 3, and so on. And I'll use LPL to refer to the set of all of the link patterns of a particular size. So to show you how the Temperley-Lieb generators act on the link patterns, EI is this picture acting between sites I and I plus 1, so this is E3 acting between sites 3 and 4, and acting as the identity everywhere else. So with that action, we notice that site 2 is connected to site 7, and then site 3 is connected to site 4. So we can rewrite that as this pattern, and that's it. That's the action of E3 on the link patterns. So the link patterns form a module for the this representation of the Temperley-Lieb algebra. Did I want to say something else there? No, that's all right. Okay, so just to give some background, some reason why you might be interested in this loop model, now that I've defined the thing, it's closely related to critical bond percolation and also to the Potts by the same sort of relationship. So in critical bond percolation, we have a square lattice of sites, and each pair of neighboring sites might be connected by a bond, or they might not be connected by a bond. And the loops can be drawn around these clusters of bonds, and they exactly form the Temperley-Lieb loop model. So anything that the cluster does, the loop does, basically. So the loops are the hulls of the percolation clusters. And it's also closely related to the XXZ spin chain and the 6-vertex model by consequence, because they've got the same Hamiltonian. Okay, so how do we calculate anything in this model? Well, the most useful object is transfer. Both cases is just a summary of what happens on the smallest repeating part of the lattice. So in the periodic case, it's a single row, and in the reflecting case, it's 2 rows connected by these strange boundary conditions. And it just gives all of the possible configurations of this row. And as a matrix, it's sending link patterns to link patterns along with the sums of weights of all the configurations that so the ground state of the transfer matrix is you can think of it as if the semi-infinite lattice is the transfer matrix having acted infinitely many times on an initial state, then the ground state is what you get at the end of that infinite process. And so this is obviously a linear combination of all of the different link patterns with components psi beta. It has this eigenvalue lambda. Yeah, and for the case that we're looking at, it's actually enough to think of the Hamiltonian instead, which is related to the transfer matrix. It's the logarithmic derivative. I haven't given you enough details to tell you what it's the derivative with respect to, but anyway, you can show that the Hamiltonian is just equal to this sum. So for each site of the lattice, there's tau, the closed loop weight, minus the Temperley-Lieb generator. And so in the periodic case, there's L terms. In the reflecting case, there's L minus 1, because the reflecting case have the action between site L and site 1, like the periodic one does. So when the loop weight is equal to 1, this is a very special point, because at that point the whole model is stochastic. This is the combinatorial of the XZ spin chain. And when that the system is stochastic, the eigenvalue of the transfer matrix is 1, the eigenvalue of the Hamiltonian is 0, and so what we really want to solve is this equation. So to find the zero energy eigenstate of this Hamiltonian, which can be done. So when tau is equal to 1, it can be shown that that the ground state is a solution of the Q-deformed Knizhnik-Zamolodchikov equation. And when the system is done in its full generality, which I haven't shown you, with spectral parameters included, you can work out what the components are as polynomials. And yeah, it's the ground state. Yes, at this value of tau. It's, yes. Yeah. So yes. Yeah, exactly. Yeah. I haven't shown you that explicitly because the observable we're looking at, we haven't used the homogeneities, but yeah, in order to do this, you need to have the homogeneities included. But it makes it easier to calculate if you include the inhomogeneities. But if you have all of those parameters set to 1, then these are the properties of the eigenvalue. The first one is that you can normalize it so that its smallest entry is 1, and then the rest of them are positive integers. It means positive. So the smallest component of the eigenvector corresponds to this link pattern, which is known as the fully nested link pattern. And the largest component corresponds to the fully unnested link pattern, which means that in this stochastic process, this link pattern is the least likely, and this one is the most likely. So this second picture here is for an odd size system. So in the periodic case, there's more than one of each of these pictures. So there's more than one link pattern that looks like that, and there's more than one looks like that. So in that case, each of them has the same weight. The components are these positive integers, and there is a whole lot of combinatorics that falls out of this model, which is what makes it so special. So this equals 1 is known as the combinatorial point because of this. So the Razumov-Stroganov conjecture, which was proved by Cantini and Sportiello, is related to this ground state. And there's also modified conjectures which haven't been proved for the reflecting case and for other boundary conditions as well. So to go any further, I just need to throw a bit of combinatorics at you so that I can define the next thing. The first thing, the most important object in this study is the alternating sign matrices. So in case some of you haven't seen this before, an alternating sign matrix is a matrix made up of zeros, ones, and negative ones, where the ones and the negative ones alternate along each row and each column, and the rows and columns must each sum to 1, which also means that they have to start and end on 1. And this is how many there are. So that's represented by the letter AN. And those are the first couple of numbers. So each permutation matrix is an alternating sign matrix. So for size 3, there's 6 permutation matrices, but there's 1 extra alternating sign matrix, which is a negative 1. 1, 2, 7, 42 numbers will come up again. So the next object is the vertically symmetric alternating sign matrices. So this is the same rules, except that it also has a symmetry around the vertical axis. So this is how many there are. And in order to give this symmetry, the matrix needs to be odd size. So this is AV2n plus 1. Then the third object is the cyclically symmetric transpose complement plane partition. Plane partitions were luckily introduced in the previous talk. I'll just mention briefly. So you can think of them as stacking small cubes inside a larger cube, or you can think of them as rhombus tilings of the hexagon. Now the cyclic symmetry means that it's symmetric under a rotation by 2 pi on 3. And the transpose complement is something to do with the cube stacking version, but you can think of it just as a reflective symmetry across these lines. So that's the CSTCPPs of even box size, and that's how many there are. So these numbers all come up all over the place in this study. So the other thing about the combinatorics of the ground state of the Temperley-Lieb loop model, that when you normalize the ground state so that the smallest entry is 1, because you're normalizing a particular way, you have to keep track of how you've normalized it. So this ZL is the sum of all of the entries. So this is the normalization. And this normalization is equal to the number of alternating sign matrices. And in the reflecting case, depending on whether it's odd or even, it's equal to either the number of vertically symmetric alternating sign matrices or the number of cyclically symmetric transpose complement plane partitions. So there is also, for the odd size periodic case, there is a rule, but the results that we haven't managed to get anything for the odd size periodic case, so I haven't bothered to define that one. And so that's the normalization. The largest component also is in terms of these numbers. So in the periodic case, it's the number of alternating sign matrices size 1 small, and in the reflecting case, from the normalization. Okay, so there's the combinatorics. So that was the introduction to the loop model. So now what I'll do is define the observable that we've been working on, and then hopefully show you some of the results we've gotten. Okay, so what are we doing? In order to define the observable, observable, first need to introduce this guy. So this is an inverted link pattern. So instead of the sites being connected by links downwards, I'm connecting them upwards instead. And the idea is I'm going to put this on top of the ceiling. So the definition is just that each site is connected to its immediate neighbor. And in the odd case, the very last site is left unconnected. And there's an obvious way to put these, put this inverted link pattern together with a standard link pattern. That's just to take the one and put it on top of the other. And I'm going to define the scalar product to be x to the number of closed loops that this forms. So as an example, take this link pattern beta, put alpha naught on top of it, and this forms two closed loops. So that's just going to, the scalar product is just going to be x squared. So then the definition of the observable is this special inverted link pattern, take an inner product with the entire ground state normalized. This is just for each component, for each normalized component, you multiply it by x to the number of forms under this scalar product, and then sum everything up. And this is the homogeneous case, so this is just an x. This generating function, this observable, it was of interest initially. Jesper Jacobsen was interested in it because it's more or less it's the boundary contribution to the entropy of critical bond percolation. So it's a pretty nice thing to know. So just to show you exactly how this whole thing works, take the reflecting case, put these this inverted link pattern on the top, and for a particular configuration, count how many loops go through the very top of the boundary. Any closed anywhere else, ignore them. Ones that go through the top, you count them with a factor of x, and then go from there. Okay, so what have we got? I'll show you the f of x explicitly in small sizes in a few slides, but this is basically the summary of the results we've got. The first thing is for a general finite size, we have explicit expressions for this observable for odd and even reflecting case and the even periodic case. And at particular values of x, it gives combinatorial expressions. This has a lot of combinatorics in it, which is what I find mostly interesting about it. In the periodic case, calculate the asymptotics exactly. The idea being to compare them with results that predictions that have been made by CFT. And in the reflecting case, I'll show you why, but we haven't been able to do the asymptotics exactly, but there are conjectured terms, conjectured asymptotics for the log term which match up with the numerics for, of L, the size of the system. Yeah, so asymptotics of F in the limit of large system. Okay, so first of all, the first two. These are the explicit expressions for f of x. Here they are. So in the periodic case, it's just a sum with coefficients to do with the alternating psi matrices. I'll define this thing in a second. As you can see, it's just a degree n polynomial where the size of the system is 2n. The reflecting case, they have these determined expressions. And the fact that they're only determinate expressions with the size of the matrix being the size of the system, up to a factor of 2, this is what makes it so hard to calculate the asymptotics exactly. Some way to get at the asymptotics of this determinant, then we would be very happy. But we haven't found it yet. Okay, so these 3 expressions are all proved. And the proofs were done by finding that they're actually the same expressions as partial sums of the ground state components that were defined in various other papers. So in the reflecting case, it was something that was defined in these papers, and in this paper by Philippe Di Francesco and Paul Zingerstan, they gave this explicit determinant formula, and both of these, and proved them, but the X actually given any real physical meaning. It just seemed to be introduced as an afterthought. They did then showed that it was a parameter that gave you a refined counting of a modification on the CST-CPPs. But it's a very complicated refinement, and it was, like I said, it was an afterthought. So the fact that we've got a physical interpretation for this X on the loop model side is like an extra step on top of what they did. For the periodic case, it was a similar thing. Again, it was the partial sum of the ground state components, and it was shown in this paper, I think, that it was that counting of the TSS-CPP, so this is totally symmetric self-complementary plane partitions. It's a different symmetry class of plane partitions, which I won't bother defining. Now, these expressions did appear in these papers, and they were proved to be some things, so I don't want you to think that the proof of these 3 things was some feat of calculation. It was mostly detective work, because it was a matter of following the thread through all of these papers to show that these expressions actually were the things that we were after. Okay. So in the periodic case, we've got this A and K. A and K is the number of alternating sign matrices of n, where the 1 in the top row appears in the kth column. So in each alternating sign matrix, the top row, well, all of the outside rows and columns actually will only have a single 1 in them. And if you refine by the position of the 1, then you get these special numbers. So these are the first few. So this adds to 1, 2, 7, 42, etc. So this is actually pretty interesting, because this expression on the right-hand side here is a refined counting of alternating sign matrices according to the position of the 1 in the top row. And we've said that it's actually equal to something on the loop, which via the Razumov-Stroganov conjecture gives you a combinatorial relationship that has nothing to do with physics. But the proof of it is via physics. So if somebody's interested in that, I have a couple of slides at the end that describe it, but I don't necessarily plan to talk any more about that. Okay, so these are the small size examples of the observable. In the even and odd reflecting periodic cases, we have 1, 1, 2, 3, 2, 7, 14, 14. Yeah. Sorry, that's the normalization. So F is normalized. Yeah. So so there's these denominators here. And if you just ignore those denominators, then you get polynomials with integer coefficients, which are nice to look So yeah, that's all I did. Okay, so the periodic case is very nice. It's very obviously the refined alternating sign. The other cases, remember these two ones are given by determinant formulas, but they also have a lot of combinatorics. So here we've got 1, 2, 11, 170, 1, 3, 26, 646, and even in the odd periodic case, which we don't have results for, there's also combinatorics. There's 2, 10, 140, 1, 4, 49. So these numbers are half-turn symmetric alternating sign matrices, and these ones are actually the alternating sign matrix numbers squared. So 1 squared, 2 squared, 7 squared, 42 squared. So as you can see, there's lots and lots of combinatorics to be found in these polynomials. And as so when I've got this arrow here, what I mean is that you divide or you divide by an appropriate power of x and then take the limit as x goes to 0 or infinity. This should actually be plus or minus infinity. It's the same in both cases. And if you take x to 0, you just get the first coefficient. If you take x to infinity, you get the last. But if you take x to be -1 or 2, you also get combinatorial numbers, which is pretty interesting. So in the x is 0 case, we've got alternating sign matrices, half-turn, vertically symmetric ones, and this p, which is not necessarily anything combinatorial, but nevertheless has an explicit product formula. So they are simple numbers, despite the fact that they don't seem to be anything combinatorial. The last ones are alternating sign matrices squared, CST, CPPs, vertically symmetric ones. When x is 2, we have, again, the vertically symmetric half-turn ones. And when x is -1, we have, again, vertically symmetric, or vertically and horizontally symmetric alternating sign matrices. But in these cases, there is a dependence on the parity. So it's not an even system size, it's a system size that's divisible by 4 that you have to be careful of. Okay, and I've got all these boxes next to things. So the ones with ticks in them are the ones that have been proved. The other ones are either very obviously true but just not proved, or they're just and this question mark is numbers that we haven't actually been able to figure out yet relate to alternating sign matrices, which doesn't seem like such a stretch at this point. Okay, so those are the combinatorial expressions. How am I doing for time? Okay, cool. All right. So that's all the finite stuff, but what we've managed to do as well is to get some asymptotics in order to compare it with physics. So in the periodic case, sorry? Yeah, asymptotics of f. So this is a polynomial without a constant term. So a nice thing to do is just to divide by one of the x's. And if you do that, then this f tilde, this new function, satisfies a second order differential equation. And its initial conditions are given by these things here. So we have initial conditions at 0, 1 as well. It's true. It's infinity. Okay, so the second order differential equation suggests that you might want to take this form for the asymptotics, for the asymptotic expression. So we have starting with the power of n, then a constant, then 1 on n, then capital N? Oh, right, it's L is 2n. Because it's a periodic case, it's even, so L is 2n. Okay, so if you take this exponential form and put it into the dE and then expand in powers of the differential equation for S. Now, you'll notice it's a first order differential equation. It's quadratic in the first derivative, but it's first order, so it's actually very simple to solve. So once you have that solution, you look at the next coefficient, and then you get this equation which has S0 and S1 in it. But by now you know what S1 is. Plug it in and solve for S0, and again, it's quite easy to solve. And 1 gives you a similar thing. It gives you a dE that has S0 and S1 and 1 along. But by now you know these two, so you can solve for S -1. And in each case, it's a first order differential equation, despite the fact that we started with a second order. So it's not too hard. Oh yeah, and so on. Okay, so just looking at the very first one, I won't do the rest of them, just the first one. So this is the leading order asymptotics of f of x for the periodic case. So we have this differential equation, quadratic, so we can solve for the first derivative, and we get these two solutions with these initial conditions. There is also an initial condition at -1, which I worked out last week, so I haven't put them in the slides. Okay, so two possible things, some initial conditions. Problem is that the negative solution is incompatible with the first three initial conditions, and the positive root is incompatible with the last one. So there's not one single solution to this thing, there's two. It's got to be not differentiable somewhere. So these are the two solutions. There's the red one is the -1, the blue one's the positive one. And these dots here, 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 here are the initial conditions. So at 0, 1, infinity, and -infinity. And the initial condition at negative is right there on the intersection. So it has to be not differentiable somewhere, but if we want it to be continuous, then it seems that what we should take is the red one up to x equals -1, and then the blue one for x bigger than -1. And that's actually what we find the data follows. This is the, yeah. This is either S1 or the exponential of S1. I think it's e to the S1. So it's the solution of this, or e to the solution of this. I think it's just the solution. By now I've forgotten. Yeah. So this sort of flying bird shape here is exactly what we find the data follows. So this data from system sizes of 200 to 400 with all these dots, and they follow the pattern of the blue line to the right of -1 and the red line to the left of -1. So -1 is a special point. That seems to be where things fall down. And if you're worried about f of x being positive, then -1 is where, left of -1 is where it stops being necessarily positive. So for S0 and S-1, for all of the lower order terms, we get sorts of results. But it's the same sort of thing. A function on the left of -1, another function on the right of -1, and the data matches them. So, for the reflecting case, the ones that go through the top of the lattice, yeah. Yeah, it's, I'm trying to, yeah, I'm just trying to think, because usually it is, but since the weight is different at the top, I guess, yeah, I'm just trying to work it out. If you're acting with the Temperley-Lieb generator on the top, then you would be introducing a, no, not necessarily. Because if you act with the Temperley-Lieb generator on this, then you'll get a weight of tau, which is set equal to 1. X is another, it's a special fugacity that you give to the loops that go through the top of the lattice. So it's not necessarily related to the algebra, it's like a something. Okay. Yes. Yeah, so for X positive, everything is perfectly fine. If you're insistent on things being physical, then there's no issue. But yeah, we're interested in negative things as well because of all of the combinatorics that comes out. So. But what it does seem like the f of x is positive for x bigger than -1. Yeah. I haven't quite been able to prove it. It's definitely positive for x bigger than 0, but between -1 and 0, it looks like it's also positive. Sorry, tilde f. Yeah, f divided by x. Right, so yeah, for f of x, the statement is simpler for tilde f. Okay, so for the reflection case, like I said, since we've got these determinant formulas, we haven't been able to do any exact asymptotics, but Jesper has been able to come up with some predictions that the data matches. So again, these are the expressions for the reflecting case. And we define this tilde f. So it's defined differently in the even and odd cases because in the case, so way to think about it is that in the even case, you're always going to have at least one loop going through the top. So that means that there's not going to be any constant term. So this determined expression actually produces no constant term. In the odd case, you can have 0 loops. You can have a case like this. So There's just a single unpaired strand that goes through the top and then keeps on going without producing any closed loops. And so F tilde is the thing with a constant term. So in the even case, we divide by x, and if in the odd case, we don't. So then F tilde is expected to be similar to the periodic case, so again with the n term constant, 1 on n term, but it's also expected to have this log term by CFT arguments. So this, the reflecting case to the periodic case, this is the very first one. It is expected to be equal to the periodic case, and that's what we find. So these dots are data from the reflecting case now, and to show you, to convince you that this is not just the same picture repeated, there's this dot here at -1, which is a result of my code not being quite up to scratch at x equals -1. So the functions are the same, but the data is from the reflecting case, not the periodic one. And then for the log term, things get a little bit complicated. If you parameterize the parameter x by this function of r, so as r goes from 0 to 3, x goes from infinity to -infinity, then the conjecture that Jesper made with EFT arguments is that the function should be, for the even case, it should be this. And again, there's a difference between x bigger than -1 and x less than -1. So that corresponds to splitting this parameterization at 5 on 2. So to the right, it should be this. To the left, it should be that. And for the odd case, it's something. And the data matches it. So for the even case, we have the two functions not matching up at -1. Functions. Okay, and we can also get data for the lower order terms, but since we don't have predictions for those yet, that's not quite so interesting. But here are the dots anyway. But as you can see, something funny always seems to happen at -1. -1 is a strange point. Okay, so I guess I'm very under time. But there's lots left to do. So the first thing to finish off is to finish ticking all those boxes in that grid. And the second one is obviously to try and find a way to do the asymptotics of these determined expressions. And an obvious outstanding problem is the one of the odd size periodic case. So for the reflecting case, we've managed to do things for the even and odd sizes, and they're almost exactly the same. But for the odd size periodic one, for some reason, there's just no idea about what this function should be. I'm always interested in trying to apply other boundary conditions to it to try and figure out how to define it in terms of the boundary conditions. And when tau is not equal to 1, what happens then? So the combinatorics of QKZ, the Q-Knizhnik-Zamolodchikov solution still holds when tau is not equal to 1. It's just that it's no longer related to the ground state of this loop model. So it might be interesting to deviate from the loop model and just try and work out stuff about this generating function in the QKZ solution for general tau. This combinatorial identity that I mentioned about alternating psi matrices that has nothing to do with physics, there is a proof, but it's not a combinatorial proof. So it would be interesting to try and find a combinatorial proof of that. But again, that's nothing to do with physics. Of course, the generalized Razumov-Stroganov projector is still open and somebody has to prove it. So that would be nice. So that's as far as we've gotten. Thanks.